Alright, hello everybody. We're at the end of section 9.2. We've already learned how to find the antiderivatives of 1 over x and e to the x. We just learned how to integrate functions that are compositions with the linear function ax plus b. And now what we're going to do is we're going to use the substitution method. The substitution method to evaluate integrals of this lovely form right there. Alright, now I want to get right into this because what we're doing today is pretty complicated and it's going to require a lot of attention to detail on your part, both in terms of the methods that I use, the reasonings for those methods, and the notation that's being used. All of that you got to pay extra attention to in this lesson. Okay, so we're using the substitution method. Now the first thing I wanted to explain to you is how when we're using the substitution method, in a real sense, what we're doing is undoing the chain rule. Now you remember the chain rule for derivatives, okay? This function right here is very close to being something you would get from taking the derivative using a chain rule. I want to explain that real quick. You might remember that the chain rule is for finding such a derivative as this, the derivative of a composition of two functions. Okay, so where you've got an inner function and you've got an outer function. And you might remember that we said that when you use the chain rule, you take the derivative of the outer function times the derivative of the inner function. And that's almost exactly what this expression is right here. It's not exactly the derivative of the outer function because you don't see an f prime right there, but you see an inner function here, and then you see the derivative of that function off to the right. Okay. Now, in a real sense, what we're trying to do is we're trying to derive or find the integral of a function where there's a composition involved. And when you look over this, there's actually two functions here. There's 3x squared and there's e to the x cubed. E to the x cubed is a composition, right? It's e to the x composed of x cubed. Now, I don't want you to think about product rule here, even though there is a product. But what I want you to think about is the inner function of that composition, x cubed. What's the derivative of that? Isn't it 3x squared right here? Alright, so we have a situation where we've got a composition of two functions being multiplied by the derivative of the inner function. And that's exactly what this pattern is here. You have a composition of two functions being multiplied by the derivative of the inner function. And whenever that's a scenario that you're facing, you can use the substitution method to make the integration pretty simple. This looks complicated, but through the substitution method, we're going to make something that looks very simple that you're going to be able to integrate with no problem. Alright, again, pay very careful attention to what you're doing. The idea with the substitution method is we're going to try to take a complicated looking function that we don't know how to integrate, and we're going to turn it into something simple looking that we do know how to integrate. And we're going to do so by taking that inner function when you've got a composition and replacing that with some simpler value. And that simpler value that we're going to use every time is going to be u. We're going to say let u equal x cubed. And you'll see the purpose of that in a moment. You'll also see the purpose of this in a moment. Once you let u equal that inner function x cubed, I also want you to find the derivative of u with respect to x. Notation very, very important here. Alright, du dx means the derivative of u with respect to x. And when I find the derivative of u with respect to x, it's 3x squared. Okay, now if you look back at your original problem, we've got an x cubed there, our inner function. Whoops, didn't mean to write that. Got the x cubed there for our inner function, and we're saying u is equal to x cubed. So in a moment, instead of e to the x cubed, we're going to write e to the u power right here. Also, you see that the derivative of u with respect to x is 3x squared, and we already said that 3x squared was the derivative of x cubed right there. I'm going to be able to replace this 3x squared with du dx. Now I'll explain why that's necessary as I go. Alright, so watch me rewrite this, and I'll skip over the 3x part for a moment. Let's rewrite e to the x cubed as e to the u power, and let's leave the dx right there. All right, we're trying to rewrite this expression so that it only has u's in it. And so instead of writing 3x squared, I'm going to write du dx. Now you might say there's still x's in this expression, and you're correct. However, if you look at du dx times e to the u power times dx, wouldn't dx cancel when you multiply du over dx times dx? All right, you can treat that just like any other fraction. The answer is yes, it would cancel. Watch this. All right, the dx's cancel, and now I think you can see how I can rewrite that expression as the integral of e to the u du if I just rearrange the remaining terms. Now that is a much simpler expression to integrate than what we started off with originally. You know how to find the integral of e to the x with respect to x, so you know how to find the integral of u with respect to u. It's just going to be e to the u power plus a constant of integration. So here's what we're going to get. All right, and then there is one more step, but we've done the tricky part here already. The original problem wanted us to find the derivative with respect, the integral with respect to x, so we need x's in our final answer, not u's. So simply at the end, when you've got e to the u plus c, replace u with that entered function value x cubed. E to the x cubed plus c is the indefinite integral for that problem that we were working on here. Great, so that's the substitution method. We obviously need to see more examples. If that one didn't make sense to you yet, pause, rewind it, check it out, and then join me on the next example. All right, again, a very complicated looking integral here. All right. What I want you to notice, though, is this. There are two functions involved. There's the function in the numerator, and there's the function in the denominator. There's actually kind of a hidden function here as well that you'll be able to see later on, and I'll point it out to you. But here's the important thing. With those two functions, one of those functions is the derivative of the other function. And hopefully you can tell that it's 3x squared minus 8x. That's the derivative of x cubed minus 4x squared minus 5. And so when we're using the substitution method, what we're going to do is we're going to take the x cubed minus 4x squared minus 5, and we're going to say let u be equal to that value. Watch. And we're also going to go and take the derivative of our new function u with respect to x, and that derivative is going to be 3x squared minus 8x. And then we're going to substitute. We're going to replace the 3x squared minus 8x with du dx. And we're going to replace x cubed minus 4x squared minus 5 with u. Go ahead and try that. Now I think you see how the substitution worked there, although it looks kind of complicated. However, all we're going to have to do to make this look a little bit simpler, a couple easy things. Du over dx times dx is still going to result in the dx's canceling. And then we can rewrite that expression this way. We can write it as the integral of du over u, which may still not seem helpful yet, because how in the world do you integrate that? But let me rewrite it one more time. How about I rewrite that as the integral of 1 over u du? Alright, you ought to see how the substitution took something that looked very complicated and gave us something that looks very simple that we know how to integrate. You know that the integral of 1 over u gives you the natural log of u, because the integral of 1 over x gives you the natural log of x. And so all we got to do is go and take that integral and then replace the u with x cubed minus 4x squared minus 5, like so. Alright, how are you feeling about that? Hopefully pretty good. Alright, we've got at least 2 more examples, possibly a third example that I'm going to throw in for you. This next one's got a pretty good trick to it. If you're ready for it, go ahead and meet me there. If not, you can watch this example again to make sure you're digesting everything that I'm feeding you here. Alright, let's go on. All right, now again we've got a situation where we've got an outer function and an inner function. Oh, I forgot to point out the outer function in the last problem. Oh well, it was the 1 over x. Anyway, you've got a composition of x to the 5th power with x to the 4th minus 1, and you're multiplying that by x cubed. The difference with this one is that if you take the derivative of the inner function, it doesn't exactly equal this other factor x cubed there. But that's going to be something we can work around. That's where the trick that I was alluding to is going to happen. Let's still start this off with replacing our inner function for the composition part with u. Go ahead. Alright, so you've got that, and this brings up the point that I just made a moment ago. We're letting u be x to the 4th power minus 1, which means that the derivative of u with respect to x is 4x cubed, but this other factor over here is not 4x cubed. Alright, so what we're going to do is recreate this function cosmetically, I suppose. We're going to change the way that it looks. And it's a pretty clever trick, but it's one that you'll understand why we used. Watch this. Alright, I'm going to leave that x cubed alone for a moment. Well, I'll tell you what. No, I'm not. What I was going to say, I'm going to do that on the next step. This x cubed, we would really like that to be a 4x cubed instead of an x cubed for previously explained reasons. And here's how we're going to make that happen. I think you would agree that what I'm going to write right here, 1/4 times 4x cubed, is equivalent to x cubed, right? Now, why in the world would I rewrite it as 1/4 times 4x cubed? Well, if I have a 4x cubed, I can replace that with du dx. I could not replace x cubed with du dx. Let me finish writing the function. Alright, so if I'm writing it with x's, I can write the end as x to the 4th minus 1 to the 5th dx still. And then on the next step, what I can do is pull that 1/4 in front of the integral sign, and I can replace 4x cubed with du dx, and replace the x to the 4th minus 1 to the 5th power with u to the 5th power dx. Now we're getting somewhere. We can go ahead and cancel out the dx's like we've seen in the previous couple problems. And you ought to be able to finish this integral up from here. Alright, so go ahead and write that as 1/4 times the integral of u to the 5th du. Use your power rule and go ahead and find the integral and check your answer for me. Alright, hope you did fine there. You can see how I used the power rule to integrate u to the 5th and make it 1/6 u to the 6th. And then I had to multiply the 1/6 with the 1/4 that was in front of the integration symbol. And so that became 1/24 u to the 6th power plus the constant of integration. And then of course replace u to the 6th power with x to the 4th minus 1 to the 6th power. Replace u with x to the 4th minus 1. Alright. Very good work if you're understanding this. If not, keep trying. Let's go on to at least one more example here. And this one, I would like you to do from start to finish. I just want to remind you that when you've got something written in radical form, it's going to be easier if you change this so it's not in radical form. But you ought to be able to use the substitution method to integrate that function. Try it out. Check your answer as always. Alright, now let me check in with you and start going over the answer. You can see where I used my u substitution right here. And you can see that I found the derivative of u with respect to x. And I didn't show this, but I think you can understand it. X squared minus 4x plus 1 could have been written as x squared minus 4x plus 1 to the 1/2 power. Alright, so I wrote u to the 1/2 power rather than writing the square root of u. And then of course replace 2x minus 4 with du dx. And then the dx's will cancel. And you're left with the integral of u to the 1/2 du. All right, and then from there, I just I increased the exponent by 1 when I integrated, multiplied by the reciprocal, and then took that and replaced the u with the x squared minus 4x plus 1, and we were done. All right, good. I do have one more example, and for the last example, I'm not going to do any talking because I'd like to give you the option to be done with the video now if you don't want to be done with the video now. And I do appreciate your attention. Hopefully you're getting all those details down. And we will work many more examples in class. But one more example here. I'll show you the problem. I won't say a word. I'll write the answer on the screen, and you can simply see if you got it right or got it wrong. All right, I'll see you in class.